Okay, this is the video that contains 4-3 notes, part 2. Now we're going to use our idea of derivatives of inverse functions and actually find a couple of new derivatives. We'll start with the exponential function, y equals e to the x. And we'll try to find the derivative of this. Well, I don't know what the derivative of this is, but I do know that this is the same as if we wrote this in logarithmic form. If I take the natural log of both sides, natural log of y is equal to natural log of e to the x, and by our power rule, not the power rule, but the logarithm rule, we can take that out to the front. So that's the same as natural log y is equal to x times the natural log of e. And natural log of e, that's asking what do you have to raise e to get e? Well, the first power, right? So this is just 1. So that says natural log y is equal to x. And then take the derivative of both sides. This is like our logarithmic differentiation. When we take the derivative of this, we get 1 over y, and then a dy dx, because I took the derivative of a y, equals 1. Then multiply the y over to the other side. So dy dx is equal to y. Whoa. Y. And of course y is e to the x. So the derivative is e to the x. And lo and behold, we have found a function that is its own derivative. This is the only function that has this property. You can put a number in front of this, like the derivative of 5e to the x is also 5e to the x because of the constant multiple rule. But this is the only function that is its own derivative. That is a very, very important result. And it will come back in word problem form when we look at this relationship right here. This says the rate of change of y with respect to x is y. So in other words, the rate is the same as the y value. And it turns out that's the kind of situation that describes money growing in a bank account or population growth in a lot of situations, things like that. So we'll come back to that. But for right now, we have this result. So let's do a couple of examples using that result. What's the derivative? Let's see. If y is equal to e to the x cubed, then what would the derivative be? Well, the derivative of e to the whatever is e to the whatever. Now, in this kind of situation, when we do the chain rule with these, this is where the x would have been, so this is like the what's inside. So I have to multiply by the derivative of what's inside, which is that exponent, which is 3x squared. Okay, try this one. What's the derivative of 5e to the cosine x? I'll just pause and try that. No, the 5 is just a number. So 5, and then the derivative of e to the whatever is itself, e to the whatever, times the derivative of what's inside, which is negative sine x. Try one more example. What's the derivative of e to the, let's see, how about e to the secant x times the natural log of x squared plus 5x plus 1. This is a product. Go ahead and try that. So the derivative is the derivative of the first. So the derivative of e to the secant x is e to the secant x times the derivative of what's inside, which is secant x tangent x. That's the derivative of the first times the second, plus the first times the derivative of the second. The derivative of natural log of whatever is 1 over whatever times the derivative of what's inside, which is 2x plus 5. Now there's your derivative. All right, so e to the x is a very special function. It is its own derivative. So there's a new one. We got it by doing logarithmic differentiation. Now, a little trickier and more to do with inverses. Of course, remember that e to the x and natural log x are inverse functions, so that is related to what we've been doing. Now we're going to talk about the derivatives of the inverse trig functions. I'm going to show you how we get them. Again, this is a means to an end, but it's important for you to see this. Okay? Looks like this. So let's say we have this function, y equals sine inverse of x, and we want to find its derivative. So find y prime. We could, this is the same if you don't want to work with the sine inverse function. Saying y equals sine inverse x is the same as saying the sine of y is equal to x. Right? That's two ways of saying the same thing. And we could take the derivative of this, right? We could say, well, what's the derivative of sine y? Using implicit differentiation, the derivative of sine y is cosine y dy dx, because we took the derivative of a y, equals 1. So dy dx is equal to 1 over cosine y. Moving that over to here. Well, that's fine, but I'd much rather have dy dx, this derivative, defined explicitly in terms of x. So let's do a little geometry and see if we can get rid of this cosine y and turn it into something with x's in it. I'm going to draw a triangle here. A right triangle. And I want you to think about this for a minute. Sine inverse of x is actually an angle, right? Usually the sine function, if you put something into it, you put an angle into the sine function, and you get its y-coordinate on the unit circle. And maybe pause here and think for a minute about what the sine function is. You could think back to our little diagrams. Here's the sine function. You put in an angle, and you get the y-coordinate from the unit circle, right? Well, the sine inverse function does the opposite. So sine inverse, you put in a y-coordinate, and you get out the angle. So that means sine inverse of x is an angle, right? Now, I'm going to carefully label the sides of this. I want this side to be x and this side to be 1. I want this to be equal to x. So what I'm thinking about here is this relationship from basic trig. You know that sine of theta will be equal to x over 1, right? Sine equals opposite over hypotenuse. But I chose those carefully so I would just get an x here. And then switching this around the same way that we switched these, that's the same as saying that the sine inverse of x is equal to theta. And there you can see very clearly that sine inverse of x is an angle, right? So let's just write that right in here, sine inverse of x. That is that angle. Using the Pythagorean theorem, we could figure out that this other side of this triangle is, let's see, this squared plus this squared would have to be equal to this squared. So doing a little bit of simple algebra, this comes out to be the square root of 1 minus x squared. And now I want to know what the cosine of this angle is, right? Y is sine inverse of x. So maybe I can just write here dy dx 1 over the cosine of y equals sine inverse x. So I'm just replacing that. And that is that angle, right? So what's the cosine of theta? Well, the cosine of that angle, which is the same as saying the cosine of sine inverse x, that angle. Cosine is adjacent over hypotenuse, and that's the square root of 1 minus x squared over 1. And now I can come back here and replace that. So dy dx is equal to 1 over the cosine of sine inverse. We just found that that's square root of 1 minus x squared. Oh, there it is. New derivative. What's the derivative of the sine inverse function? It's 1 over the square root of 1 minus x squared. The proof of a couple of the other ones of these, I'll show you the tangent function, because that's the other one. That's one that comes up an awful lot. So let's say y is equal to tangent x. Go a little bit faster with this one. Please pause if you want to stop and think about any of the steps. That's the same as saying x equals tangent inverse y. I'm going to draw my actually, I'll take the derivative here first. So that's 1 is equal to, let's see, that would be secant squared of, oops, I'm sorry. Let's go back and fix that. I meant to start with y equals tangent inverse x. We're trying to find the derivative of the tangent inverse function. So now I would have the tangent function. The derivative of that is secant squared y dy dx. And then solving for dy dx, dividing by secant squared, we've done that before in related rates problems, will give me cosine squared y over here. And now let's draw the triangle. If this is my angle here, I'm talking about the tangent function, so I want opposite over adjacent to be equal to x. So I'll make that x and I'll make this 1. Okay? Then I could say tangent theta is equal to x over 1, opposite over adjacent. And then rewriting that, I could say tangent inverse of x is equal to theta. Right? It's just like with the sine function. That's an angle. Okay? Using the Pythagorean theorem, you can find that this hypotenuse is the square root of 1 plus x squared. And now, since I want, let me go that one extra step here, dy dx is equal to cosine of y is equal to tangent inverse x, which is theta, right? Whatever that is, squared. So dy dx is equal to the cosine of that angle. Let's see, cosine would be equal to adjacent over hypotenuse, and that'd be 1 over the square root of 1 plus x squared, but we want cosine squared, so dy dx is equal to 1 over 1 plus x squared. So here's the tangent inverse function, and here's its derivative. Okay? There are 6 trig functions, but really we only need to know, we're not going to look at, you can look it up in the book if you want to. We're not going to work with the secant inverse and cosecant inverse. We will not work with those functions. We're going to work with, let me make a little table here. We'll do f of x, and here are the derivatives. We're going to work with sine, cosine, tangent, and cotangent. So if f of x is equal to sine x, the derivative, which we just proved, is the square root of 1 over the square root of 1 minus x squared. Using a very similar proof, you could show that right on this side of the page here. We just, I'm sorry, I keep forgetting to write those in there. These are the inverse functions, right? The inverse trig functions. The derivative of that is 1 over 1 plus x squared, and the derivative of cotangent. Thinking about the relationships that you know with the cos, you might guess, and you would be right, that it's the negative of this. So there's really only two of them to remember. 1 over the square root of 1 minus x squared, and then the co is the negative, and 1 over 1 plus x squared, and the co is the negative of that. Those are the derivatives of the inverse trig functions. You won't have to prove them, but now you know where they come from. And last, let me just do a couple examples with those. So let's see. Let's say y is equal to sine inverse of x squared. So then the derivative of that would be 1 over the square root of 1 minus whatever's in here squared, right? Normally if that were just an x, this would be x squared, but it was something else, times the derivative of what's inside. And you could simplify that, right? That's x to the fourth. How about this? Y is equal to the tangent inverse of e to the x. So the derivative of that would be, derivative of tangent inverse is 1 over 1 plus whatever's behind my finger squared times the derivative of what's inside, which is e to the x, because e to the x is its own derivative. Now, just to make sure that your algebra isn't too rusty, I could write that on top of the fraction now. 1 plus e to the x squared is e to the 2x. This is a situation where we multiply those exponents, and you need to be able to simplify it to that. Let's do one more. Y equals, how about e to the 3 cosine inverse 2x. And that's got a couple layers in it. See if we can get our way through that. Okay, so first level of chain rule, I've got e to the something. The derivative of e to the something is e to the something, right? It's its own derivative. Times the derivative of what's inside. Well, the derivative of 3 cosine inverse of whatever is 3 times the derivative of cosine inverse is negative 1 over the square root of 1 minus whatever's in here squared. And since this is another inside layer, I'm going to say last, and then times the derivative of what's inside there, which would be 2. So that's a few layers of chain rule there. The only thing, when you have this e to the whatever function, that inside thing is the exponent, right? It's what's up there is your inside. Okay, we'll try some more examples of those in class tomorrow. But those are your new derivatives. Now you know the derivative of the exponential function, and you know the derivative of the trig inverse functions. Oh, and you also need to know, sorry, one more thing. What about other exponential functions? What about something like y equals 2 to the x? We can use the same process, but you could probably figure this out. Maybe you want to pause and try to figure it out right now. Okay, you're back. So we'll use logarithmic differentiation. Right? I'll take the natural log of both sides, and then that gets to come out to the front. So that's natural log y is equal to x times the natural log of 2. Take the derivative of both sides. The derivative of natural log y is 1 over y dy dx equals, remember this is just a number, so the derivative of this number times x is just that number, as if it were the derivative of 2x would be 2, right? That's just a number. And dy dx, multiply the y over to the other side, so it's the natural log of 2 times y, and of course y was that, so dy dx is equal to 2 to the x times the natural log of 2. So it's like that, remember the derivative of e to the x was e to the x. The derivative of 2 to the x is 2 to the x. But since it wasn't that very special number e, there's a little adjustment factor here, right? That's like a little adjustment. Why does it come up? Because here, when we did natural log of e, that was just 1, and here we still have that factor. So real quickly, these are very easy examples, but just to get the feel for this. What's the derivative of e to the x? E to the x. What's the derivative of 3 to the x? It's 3 to the x times the natural log of 3. What's the derivative of 10 to the x? It's 10 to the x times the natural log of 10. What's the derivative of 9 to the x squared? It's 9 to the x squared times the natural log of 9, because that wasn't an e, and times the derivative of what's inside. What's the derivative of, let's see, how about 5 to the sine x? Well, the derivative of 5 to the sine x is 5 to the sine x. But this wasn't an e, so I need to multiply by natural log 5, right? And, chain rule, have to multiply by the derivative of what's inside. Okay? So those are the considerations here. Good luck. See you tomorrow.